is 14.4, arc length, and arc length parametrization, but we'll start with arc length. So the idea here is I have a curve, right? I want to know how long this portion of the curve is, or any portion of the curve, all right? The difficulty, of course, is that the curve is curved, right? So it's not just a straight line distance. So we can't just subtract, the values at 2 points, right? So it's actually kind of a hard problem, again, because curves can be complicated. Well, our vector value functions actually solve this for us pretty easily. So let's say we have a representation of this curve in the form of a vector valued function, okay? So again, the idea is you have time here, and then you have the corresponding positions at those times on the curve. Okay, so you're thinking of this as driving along a road, right? You want to know the length of this portion of the road, right? So you take a drive along it, and then what's going to happen is, of course, in real life, you just look at your odometer, right? Between your start time and your end time, and that's going to give you the length of the curve. All right. But now what we're going to do is we're going to, of course, do it mathematically, and I'm just going to write down the answer, and then we'll discuss it. So I'm going to call it L, the length of the curve, between times t equals a and t equals b. All right. So for example, in terms of our picture, if this is time a and that's time b, that's r of a, this is r of b, right? We're finding this formula that I'm going to write down finds for us the length of the curve from here to there. All right. Okay. So the formula is going to be r prime of t dt, length of that, right? And that's it. So this is a really nice formula because, first of all, it's a one variable calculus thing, right? So you can see here, the length of r prime of t is a function, right? It's no longer a vector. So this integral is actually an integral of a function from one variable calculus. And so in a way, it's immediately the problem is reduced to something that we already know how to do, right? One variable calculus. Okay, so that's it. If you give me an r, right, that represents the curve in terms of a parametrization, right, a vector valued function parametrization, then immediately I can figure out the length. Okay, there are some disclaimers. We'll talk about them in a couple of seconds, but that's roughly the general idea. Okay. All right. Now, don't really like to give formulas where that are unexplained. So let's think about this. Why this formula makes sense. So this term right there, that's a speed, right? R prime was the speed, or sorry, absolute value. R prime is the velocity, right? And then we're taking the length of that, so we get the speed. Okay, and then here dt, right, represents kind of like a multiplication of time, right? So what we have is speed times time, right? And that's, of course, going to be distance, right? So if you're driving 50 miles per hour and you drive for 3 hours, you've driven for 150 miles. Okay, so it makes sense that this thing over here on the left-hand side of the equation represents something to do with distance. Okay, all right. Now, of course, if you want to get more into it, you can go all the way down to looking at the definition of the integral, right? Let's do that at least a little bit. I don't want to, again, for this class, go into too much limit stuff and all that business, but let's go down a decent distance to the point where we have delta t's, right? And let's look at what's going on. So r prime of t, right? So this is going to be, let me put squiggly lines, right? How do we calculate r prime of t? We look at r prime of t and then plus a small distance in time, small interval in time away, subtract r prime of t, and then we divide by delta t, right? And we want the length of this, so I'm taking the length of both sides. Okay, So what we're doing is when we're adding up, so the integral, whenever you see the integral, just like if you saw in the extra credit problem from week 1, right? The integral is adding, right? Is summing things up, right? So what you're doing is you're summing up a lot of tiny little speed times time calculations, all right? And in terms of the picture, what's going on is if you have a curve that's curved like this, you're taking small time intervals. So let's say we're zooming into the curve. You're taking small time intervals, and then you're calculating, if you look at this expression right there, right there, right? You're calculating these vectors, right? The length of those vectors. Okay, and the deal is they're straight, right? So it's easy to calculate. In fact, you can see it's just a difference, right? But as you add things up, you get the length because when you zoom in, which is what's happening when you take small delta t, when you zoom in, the curviness of the road kind of disappears, right? So for example, if this picture, if we have a picture, far away from Google Maps, we see a road might look very wiggly, right? But when you zoom in, if you're actually physically standing on the road, right, to your point of view, the road looks pretty straight, right? 10 feet in front of you, 10 feet behind you, it looks very straight, right? Even though, again, overall, in the global view, it's very curvy, right? So what that's saying is basically when you have delta t very small, the road looks very straight. And so your simple approximations of the length of the road works pretty well, okay? So this guy in here that I've boxed roughly represents the road, right? Even though it's just a kind of like a straight line calculation, okay? All right, so this guy over here times delta t represents distance, right? This represents, let me do it like this. This slightly curved portion of the road is represented by this distance from this point to that point, okay? And what you're doing is you're adding up all these kind of straight line distances. That's what this guy right there is, all right? Okay, and again, if you actually sit down and do this with a small delta t, right, whatever, delta t equals 1/10, you're not going to get a perfect equality in your computation, right? Because you can see even here I'm missing some of the curvature of the road, so I'm not going to get the exact length. But again, as delta t goes to 0, right, as you zoom in closer and closer and closer, your calculations get more and more and more accurate, right? And again, in the limit, which is exactly what the integral is, you get the exact value of the length of the road. Okay, so that's the rough idea behind this formula here. But I think in general, if you just kind of keep in mind this speed times time, right? And of course, when you're talking about this stuff inside the integral, you're doing it over a tiny, tiny bit. And so you have this integral representing adding up all those tiny bits, right? That's I think probably a decent enough explanation that explains all the individual portions of this formula. Okay, now I said there was a disclaimer here for this formula, and that's if you take, so we said we're starting out with a road, right, a curvy road, and we're taking a parametrization of that road, right? So here's t, and our picture was something like this, right? If this is t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, we kind of implicitly assume, well, r of 0 is here, r of 1 maybe is here. We've driven pretty fast, I guess. R of 2, maybe we slowed down, is here. R of 3 is here, right? R of 4 is here, right? We're kind of driving in a continuous motion from here to there to here to here to there, right? If our motion is like that, then we're pretty much okay. The formula works. But imagine a situation where we have a curve and our parametrization instead is like this: 0, 1, 2, 3, 4. Here's r of 0, right? Here's r of 1. Here's r of 2. But then here's r of 3. We go backwards, so our kind of motion is we're driving in this direction, right? As we go from time 0 to time 1 to time 2, and then we turn around, right? So again, R represents motion, so certainly we can have a parametrization that turns around, right? So here, let's say is R of 3, right? So as time travels, we're going 0 to 1 to 2, and then we turn around as we get to 3, and then maybe we continue turning, continue in the backwards direction along 4, right? So what's going to happen is we're going to end up maybe here. And our length calculation that I originally said was the length, right? I even called it L over here, is actually not length of the curve, right? Again, what we're looking for is the length from here to here, right? That length of the curve. But what we've actually calculated in this second example down here is distance traveled, right? So if we do that integral correctly and carefully, we're actually going to get the distance traveled. So the length of the curve from here to there, and then plus the length of the curve from here to there. Okay, so we're going to be calling it length. We're going to be a little sloppy with that. Traditionally, we usually are. The book calls it length. But in actuality, you should more accurately think of it as distance traveled. All right, we're calling it length because most of the time we're going to be using this in terms of, for example, finding the length of a curve, in which case we would always choose a parametrization so that it doesn't double back. All right, but you do have to be aware that if your parametrization does do something like this, doubling back, you're not actually getting the length, you're actually getting the distance traveled. All right, and it doesn't have to double back for there to be problems. Imagine if you had a crazy curve that wasn't differentiable, right? Then you're going to have problems in terms of the formula in the first place because you have your speed here. Okay, of course, we're not going to deal with that kind of stuff in our class, but it's good to note that there are situations where you do have to be a little careful. All right. So again, if you are asked to find the length of a portion of a curve, you need to parameterize that curve. Where, for example, time equals 0 starts at the first endpoint of the curve of interest, and then your second point, another point corresponds to the last point, and then you need everything in between to not double back, right? In short, okay. All right. What's a sign that you might be doubling back? Well, you can see that R prime is going in one direction, right? When we're going forwards, R prime is moving in this general direction. R prime is moving in opposite direction, generally, as you double back, right? So what's happening is there's a point where R prime is 0. So, be aware of that, right? If you are doubling back, you're going to have a point where R prime is 0. If R prime is never 0, then generally you're going to be okay. Okay? Because that means you couldn't have turned around, right? In order, maybe think of it like this in terms of motion, for you to have doubled back, that means you have to stop and turn around, right? So your velocity has to be 0. In other words, R prime has to be 0. So that means R prime equals 0 is an indicator of a possible problem in your parametrization. Now, it doesn't necessarily mean there is a problem, but it means that there might be a problem. Okay? All right. Let's move forward. So from here, so that's it. That's it for length, right? No problem, right? You want a length of curve, parameterize it, do the integral, parameterize it carefully, do the integral, the length integral, all done. But now let's get more advanced. So let me introduce a new function. I'm going to call it S of t. Oh no. Sorry, let me pause this and figure this. All right. Oh no. Okay, sorry about that. So let's introduce a new function. Okay, so let's introduce a new function, S of t. We're assuming here that we have a parametrization of a curve, right? Or a vector value function that, again, represents a curve, r of t. So we're starting out with an r of t, right? From this r of t, we can define a function s of t. It's just a one variable calculus function. It takes the parameter t and spits out a number, okay? And that number is going to be integral from a to t r prime of t dt. All right. Okay, first of all, this is exactly the formula for the length, right? If we go all the way back up, we look at the length formula right here, right? R prime of t dt. We were integrating from t equals a to t equals b, right? Which meant that we were getting the length of the curve between r of a and r of b. Okay, so again, that length right there. Okay, so now my new function is defined with the same formula, integral of r prime of t. But now we're integrating, we want a function of t, right, with the parameter t, with the variable t. So instead of integrating from a to b, in which case we just get a regular number, we can integrate from a, which is a number, some number, to the variable t. Okay, if this always looks a little weird to a lot of people. So if this kind of blows your mind, put in a different letter here for t, u or something like that, and maybe it looks a little less weird, right? Because in that case, then you only have one occurrence of this variable t in the expression. And in fact, these t's in here, the r prime of t and the dt's, are just dummy variables, right? You can name them anything you like. They always integrate away once you plug in the two integrands of your integral. So the point here, the important point here, though, is that your variable is t. So this guy here gives you an actual function, right? So for example, s of a is equal to integral a to a r prime of t dt, and that's equal to 0, of course, right? Because you're integrating over no region, right? And integrals are area, and so you're integrating over an interval of 0 length, so there's not going to be any area under any curve. Okay, s of whatever, a plus 10, right? That's going to be a to a plus 10 r prime of t dt, and that's going to be equal to something, right? And you can calculate it. And again, it's just a number because once you've integrated and you plugged in the integrand, you get a number, right? So I really want to emphasize that from this current point of view, s is a regular one variable calculus function, okay? S of b would be equal to a to b r prime of t dt, all right? And that would be equal to something, okay? All right, now what does this function represent? Well, if you look at, again, this right-hand side here, this is just a length, or I guess more accurately, I should probably say distance traveled, but I'm just going to write down length of curve between time A and time B. Right? It's exactly the length formula that we saw above. Okay? And so our general formula, s of t equals integral a to t r prime of t dt, our general formula for this new function s is the length of curve between times a and time t. Time a and time t. Okay. All right. So this is going to be a very useful function for us. But before we do anything with it, let me do an example, because I actually want to take I want a concrete example of this right-hand side, what it might look like, and then we'll see some interesting things pop out of this. Okay, so let's start with a parametrization. R of t is, let's say, 2t plus 1 minus 3t plus 5, comma, let's say 4t. All right, so this is just a length. This is just a parametrization of a line. But let's start simple. And if you notice the homework, a lot of the parametrizations in the homework are relatively simple as well. And the only reason for that is because if you look at this formula above for s, or look at the length formula, you're integrating something r prime of t. If r is complicated, the integral of r prime of t is going to be complicated, possibly complicated. You have this absolute value, right, or the length of the vector, which makes you pop out oftentimes square roots. And so what happens in practice is that you're going to have integrals which are pretty nasty. So that's why a lot of the homework problems are relatively simple, just because they want you to be able to do problems which are actually integrable, so that you can actually see some numbers pop out. All right, but you can do all of this, with very complicated curves and parametrizations. It's just that somehow you have to figure out the integral. Okay, so we do a simple example. This is a parametrization of a line, and the velocity vector is relatively simple. And again, the whole point of making it so simple is so that we can actually easily do the integral. All right. Okay. So again, in general, right, if it's not a line, this guy is going to be, this r of t right there, that's going to be a very complicated expression. All right. Okay, r prime of t, length of that, sorry, this is r prime of t, of course. That's going to be square root 4 plus 9 plus 16, which is square root of 29. All right. And again, in general, this expression right there is going to be really nasty. It's going to have t's in it. It's going to have a square root in it, which makes, again, the problems hard. But I want to do a simple example. Okay, so the new function that I've defined, s of t, a to t, r prime of t dt, is equal to integral a to t of just square root 29 dt. All right, and nothing could be easier than that. That's just the square root 29 t from a to t, and so that's just going to be square root 29 t minus square root 29 times a. All right. Okay, so my conclusion, let me just write this down here. S of t is equal to square root 29t minus square root 29 of a. Okay, so again, this represents length of curve between times a and time t, right? Or again, more accurately, distance traveled between time a and time t. Okay, let me look at a few values and then look at the corresponding points on my curve. All right, so let me do a tiny little chart here. Okay, so we've said the start point was time equals a, right? Or another way to say it, when time is equal to a, s of t is equal to 0, right? You can see s of a is equal to root 29a minus root 29a. But let me actually do this example where a equals 0. Let's do, just for simplicity's sake, all right, a equals 0. Okay, so then my s of t would be just root 29t. All right. Okay, let's do a tiny little chart. S here. When s is equal to 0, right, t is equal to 0, right? So I'm actually kind of going backwards here, right? I'm starting with s. I'm saying when s is equal to 0, when this left-hand side is 0, what should the right-hand side be? The right-hand side should be 0, right, to make the left-hand side 0. So s equals 0, there's this correspondence with t equals 0. And this correspondence is just through the function, through the definition of the function. Okay? All right. In terms of the picture, if we now pass from t equals 0, right, if we pass using r, the vector valued function r, right, r of 0, that's going to give me a point on the line. Okay? All right, let's do a second one. S equals 1. That's going to correspond to, again, through this function right here. When s is equal to 1, right, when the left-hand side is 1, what's the right-hand side? It has to be 1 over root 29. Okay? All right, so that corresponds to a second point on this line. Let me draw the same line. but we've traveled a little bit of distance, so we're here. Okay. All right, as opposed to we were right there. Okay, I should label this. This is r of 0, right? And this guy here is r of 1 over root 29. And this guy was r of 0. Okay, so we've traveled some distance. All right, s equals 2. So again, we're kind of going backwards. If I have the output 2, right, the left-hand side is 2. What was the input? It was 2 over root 29. And again, if we plot this, we had started out here, then we moved to here, and then now we're here. Okay, so we had traveled kind of in this distance here. All right. Okay, or in that direction. Okay, now let's look at this. Between s equals 0 and s equals 1, how far did we travel? We traveled a distance of 1. Right? That was the whole point of s, right? The outputs of s represents the length of the curve, right? Or the distance traveled between time t equals, in terms of s equals 0, between t equals 0, and then s equals 1 is t equals 1 over root 29. All right? But again, what I'm doing right now is I'm kind of skipping over the t. All right? So I'm saying s equals 0, in a way, I'm going to correspond that with this point on the curve. All right? I had to find that point by passing through t. But s equals 0 corresponds to this point. Now s equals 1, I'm skipping again over the t. S equals 1 corresponds to that point. All right? So between s equals 0 and s equals 1, I've traveled from here to here a distance of exactly 1. Right? That's, again, the definition of s. And then now, s equals 2, right? Again, just kind of passing through this t business, I'm right there. Right? So I've traveled exactly a distance of 1, right? Since I was at s equals 1, again, because of the nature of the formula for s. Okay? So if I do this kind of pass through, I skip over this middle bit of t, right? What I can see is a new parametrization for my line, right? This is exactly a parametrization, right? When s equals 0, I'm giving the output of my new parametrization is this point right there. When s is equal to 1, the new output of my function the output of my new parametrization is right there. When s equals 2, the output of my new parametrization is right there. Okay, so again, this new parametrization, I think our book likes to call it R1, or at least in an example it calls it R1. It has the variable s, right? Because my inputs are this far left column on the side. Inputs are s. Outputs are on the same curve, right? It's on the same curve, but it's a motion that's moving at velocity 1, right? R of 0 to, s equals 0, I'm here. S equals 1, I've moved a distance of 1. S equals 2, I've moved a distance of another 1. Right? So the distance here, distance traveled for my new parametrization is always in perfect correspondence with my time calculation, with my time inputs, right? So if I look at where if I look at, let's say, s of 3 versus s of 5, right? And I compare the outputs for my new parametrization, the arc length of the curve between s of 3 and s of 5 is exactly 2, 5 minus 3. Okay, so this is an arc length parametrization. It's a very special kind of parametrization because, well, it's one way we can say it, again, is it's a parametrization where the velocity, or this, I should say speed to be more precise, where the speed is always 1, a constant of 1. Okay. All right. And again, the inputs correspond to exactly distance traveled. Okay. All right. So these kinds of parametrizations are super, super powerful, both in terms of actual applications and in terms of theory. We'll talk a little bit about some nice theoretical stuff toward the end. But this kind of parameterization is super powerful. Now, the way I've done it right now, right, is kind of ridiculous because, I've done one individual s equals 0. I figured out where it was. I've done one individual s1. I figured out where it was. I've done one individual s2. Figured out where it was. Obviously, we want a nice general formula, right? When I plug in, s equals whatever, 59,000, what is R1 of 59,000, right? So let's figure out the formula. Well, we've actually kind of done it here, right? In our original calculations, when s is 1, we figured out that meant that t had to be 1 over root 29, all right? And when t is 1 over root 29, if we pass using our original parameterization r, we're looking at the point r of root 129, right? And so it's getting a little messy there, so let me just write down exactly what I just said. S equals 1 corresponds to t equals 1 over root 29. And this was through our original formula that s of t was equal to root 29t, right? And that formula came from the definition of s, directly from the definition of s, okay? All right, so s corresponds to t equals 1 over root 29. And then we use the function r that we originally defined, right? And the point we got was r of 1 over root 29. Okay, just plugging in t, right? Nothing fancy there. And so if we look at our original formula, I guess I should write that down as well. R of t was, and let me scroll back up. Here we are. 2t plus 1 minus 3t plus 5. 2t plus 1 minus 3t plus 5, and then 4t. Right? So we actually have that s equals 1 corresponds to, again, I'm just going to write down the same thing, t equals 1 over root 29. And then that goes to 2 over root 29 plus 1, comma, minus 3 over root 29 plus 5, comma, 4 over root 29. All right, so we can actually calculate, input s. Our new parameterization gives me literally this output. Sorry, input s equals 1. Our output is this number right there, or this position right there, or that vector right there. Okay. Now, again, we wanted a general formula. How did we do this kind of conversion from here all the way to there? We used s of t equals root 29t, right? And probably the way the best way to think of it now is not to write s of t any longer, just to write s equals root 29t. Okay, because we want to kind of think of s as a parameter, as an input. So if we write s of t, things can look very, very confusing. So now I'm just going to drop the s of t and just write s equals root 29t. Okay, and then I can easily see my correspondence, right? When s is 1, how did we get t? Essentially, we solved for t, right? So here, when s is any number, how do I get t? I solve for t, right? So this means t is equal to s over root 29, okay? So ultimately my parameterization is if I'm at the position s for my new parameterization, right? If I'm at time s, that corresponds to time t equals s over root 29, and that corresponds to, if I use the original parameterization r, I'm going to try to not make it as squished as above. Where was it? Here's my parameterization, right? So it's just 2 times t, which is s over root 29, comma, minus 3 times s over root 29, plus 5, comma, 4 times s over root 29. Okay? So in this way, I get a formula for my new parameterization. Input s, output this guy here. And we've kind of passed through the t to go from here to here. Okay, the t is no longer necessary. The r is no longer necessary. All right, so ultimately my new parameterization, r1 of s, is equal to this guy right here, 2s over root 29. I think there was a plus something actually up there, right? Plus 1. Sorry about that. Plus 1, comma, minus 3, s over root 29, plus 5, comma, 4s over root 29. Okay. So this is how you actually, in practice, can get the formula for your new parametrization. And again, we're calling this the arc length parametrization of, in this case, a portion of a line. Okay. All right. And again, it perfectly represents length or distance traveled, right? Okay. Now notice that in this example, we started with a parametrization r of t, and then we got our arc length parametrization from that, right? Now in practice, that's what you're going to do. So in practice, a lot of times what you want is an arc length parametrization. But to immediately figure out an arc length parametrization right off the top of your head, just from the beginning, is not easy, right? But and oftentimes finding a parametrization is easy or easier, right? So in practice, we often do exactly this procedure where what you really want is an arc length parametrization of your curve. It's too hard to find in one step. So you first find a regular parametrization r of t, and then you use this procedure above to get our arc length parametrization that we actually want. All right. Okay. So in the homework, you'll be doing exactly this thing, right? They'll give you, for example, a curve. Let me write down, right? So here's a curve, y equals x squared, right? In the plane. By the way, all the pictures I've drawn today, everything is in the plane, right? Oh, actually, the line example was not in the plane, so we're all set. But I just wanted to say that everything works here, whether you're in the plane or whether you're in space, all right? Or whether you want to work in 4 dimensions and you're talking about curves in 4 dimensions. All the formulas work exactly the same, all right? Okay, so let's say you want to find an arc length parametrization of y equals x squared. And let's just, to not make our lives more complicated, just a portion of y equals x squared where x is positive. All right? So you want a parametrization of that guy right there. Arc length parametrization, right? So how would you do it? Well, again, you're not going to figure one out immediately, just straight from the top. So you start with a parametrization, right? So r of t, again, when you have a graph, right, y equals something, the most simple parametrization to come up with is t comma t squared in this case. Okay? And then from here, you can get your r1 of s using the procedure that we just talked about. Okay? All right. Notice one thing here, and you'll see this in the extra credit on the homework. We decided to start out with this particular parametrization, but if we had decided to start out with a different parametrization, q of t equals, let's say, square root of t comma t, right? Which again describes the same curve, right? Again, we're looking, this is why I wanted just x bigger than 0, so I could do both of these. This describes the same curve, just in a different way, right? It's a different parametrization. It's a different way of driving along the same road, right? However, if you go through the same procedure and calculate, sorry, I guess I would call it q1 of s, you would actually get the same parametrization. All right? Provided, of course, you had the correct lower integrand, right? To make sure that you're actually starting at the same point. Okay? So, for example, you're both starting at t equals 0. All right? Okay. So I'll let you play around with that, this example. But of course, you should get the same parameterization, same arc length parameterization. All right. So what happened was, again, just kind of in terms of the concept, if we had our original r of t, let's say this was our curve, right? Here's time interval of 1. Maybe our original curve, we're driving really fast, right? Between time 0 and 1. And then we're slowing down, right? And then we're driving really fast again, something like this, right? So our new parametrization what we've done is we've kind of slowed down. So this was our parameterization with S, and this is our new parameterization R1, right? The idea is that through the formula, S of t equals, like in our particular example, through this formula, t equals S over root 29, what we've done is we've kind of slowed down in a way when R was going fast, right? And then we've perhaps sped up when R was going too slow, so that everything now is kind of even-sized intervals when you plot out the points, right? S equals 1, 2, 3, 4, it's going to be evenly distanced on our curve, right? As opposed to unevenly distanced over here with the original R of t, okay? And you can see that in the formula because, right, what we had here was our velocity was root 29, right? So now what we've done is we've divided by root 29 to slow ourselves down to make it so that everything is actually going at the correct pace, okay? By the way, what do I mean by correct pace? Of course, the way we've set this whole thing up, R1 of S prime is equal to 1, right? We're driving at speed 1. Okay. Nothing new, but it's very worth it to emphasize this, that basically the whole point, or one way you can think of it, is the whole point of doing this arc length parameterization was to get a new parameterization that had this property right here, right? That the speed was equal to 1. Okay. All right. A note about kind of some pitfalls. Notice that if our original parameterization did something like turning around, then this new parameterization is not going to necessarily describe length, right? That's why sometimes I try to be a little careful to talk about distance traveled. For example, if R, let me do this like this, started here, our original parameterization that we base our S on, it moved to here, and then it turned around, right? Then ultimately, when we do our S, right, so this is maybe S of 0 would be, let's say we actually, let me exaggerate this. So let's say we not only drive backwards, but let's say we drive back to the same location, all right? So let's say that this one here, our start, corresponded to t equals 0. And let's say at the end, this corresponded to whatever, t equals 10, right? Well, what's going to happen is that S, when you try to solve, right? We had a formula S equals t over root 29, right? Well, in this situation, S is going to be some more complicated function of t, right? And when you try to do the correspondence, there's actually going to be 2 points of t corresponding to each S, right? So it's not going to be this one-to-one correspondence where each t corresponds to a single S. And so the whole thing is going to break down. The whole idea of doing the arc length parameterization using this particular R of t is going to break down, all right? So you do want to be careful. You can't just randomly pick any old parameterization R of t to start out with, all right? Imagine, so this is a very exaggerated example where you're actually just driving all the way back, right? In which case, again, S is going to, there's going to be 2 different times S that correspond to the same time. But what happens if your t does something like this, right? You're driving this way, and then suddenly you just stop, right? So maybe this took time 1, this took time 2, time 3, and then you stop for like 5, for time equals 0, 1, 2, 3, 4, 5, 6. Let's say you stopped, right? Then again, you're going to have problems with this correspondence, right? Because you're going to have many times where you're at this location. And so, what's going to happen with S? You're going to have trouble with that. Okay, so same issues that we talked about earlier, you're going to have here. Okay, so be a little careful of that. And again, an indicator of a problem is that r prime is equal to 0. All right. Okay. Let's see. By the way, let me emphasize again, in my example above, what I did was I looked at s equals integral from 0 to t, and it was r prime of t dt, right? I decided to start at 0, and that was so that when s is equal to 0, right, that corresponds to t equals 0, right? But if I wanted to shift my position a little bit along the curve, right, I do, again, at, right, r prime of t dt. Then when s is equal to a, I get t equals 0, right? So that does a shifting along the curve if I want to shift my time a little bit, okay? All right, so there's nothing too fancy going on there. All right, let me do one more complex computation example, just so we can see kind of something that's not just a line, right? So let's look at r of t equals cos t cubed, comma sine t cubed, right? Just to see how a typical example might look like. So r prime of t is equal to 3t squared minus sine t cubed, comma 3t squared cosine t cubed, right? And so length of r prime of t is equal to 3t squared, because we've got the sine squared and the cosine squared, right? So we get a nice simple, relatively simple formula for my speed. Okay, so let's do arc length parametrization based on this parametrization right here, s equals, and let's do it with 2 here. All right, so 2 to t, r prime of t dt, absolute value, right? That's 2 to t, 3t squared dt, right? And again, we're doing 2 here because perhaps for whatever reason, right, we wanted s equals 2 to correspond to t equals 0, right? Okay, so this is going to be integral. Sorry, I already wrote down the integral. So this is going to be t cubed from 2 to t. All right, so that's going to be t cubed minus 2 cubed, which is 8. All right, so s is equal to, my new arc length parametrization is going to be based on s equals t cubed minus 8. All right, and again, you can see when s is equal to 2, I'm going to get 2 cubed minus 8, which is 0. All right. S is 0, right? T is what? T is equal to 8. T cubed is equal to 8, right? And so t is equal to 2. Okay? When s is equal to 1, right, t is equal to what? When s is equal to 1, t is equal to cube root of 9, right? Because when s is equal to 1, you throw the 8 to the other side, you get 9. T cubed is equal to 9, right? So t is equal to cube root of 9. All right. The picture is roughly the same idea. I guess it would be, let's see, s equals 0 corresponds to t equals 2. R of, as we go through the r, right, r of 2 is going to be r of cosine of 2 cubed, comma sine of 2 cubed, which is cosine of 8, sine of 8. All right, so that's going to be somewhere like right there. Right, a little bit bigger than 2 pi, yeah. Okay, and then this guy here is going to correspond, so let me do an arrow all the way. So this is going to be that point, and this point right there is going to go to that guy right there. All right, and again, s equals 0 to s equals 1 in terms of time. That's a time interval of 1, and so this length right there is going to be 1. Okay, all right, sorry about that. So you can continue with this, and then of course the next one, s equals 2, is going to be right there, because this is s, again, represents arc length parametrization. So it's going to be evenly spaced in terms of time. All right. Okay, so how did we do this calculation correctly? How did we do it? We used s equals t cubed minus 8 to do our conversion, right? And in essence, what we did was, again, we solved for t, right? When s is equal to something, what is t? That's what we did right here. That's what we did right here, correct, in the correct version, of course, right? And so we started with t cubed minus 8 equals s, right? We solved for t, so that meant that t is equal to t cubed is equal to s plus 8, which meant that t is equal to cube root of s plus 8. All right. So that was kind of our middle step conversion, right? We have s, we have cube root of s plus 8 from here to here, and then from here to here we apply our r, right? And what was the formula for r? Again, it's cosine t cubed, sine t cubed, and so here that's our input, that's our t, right? So cosine of s plus 8 comma sine of s plus 8. That's going to be ultimately my arc length parametrization. Okay, the cube root gets cubed away, right, by our original formula for r. Okay, that's a little messy, so let me write it over here. R1 of s is equal to cosine of s plus 8, comma, sine of s plus 8. Okay. And again, we can, this is supposed to be an arc length parametrization, so if we had done it correctly, this guy here should always be 1. Right? And of course, if you stare at this, it's obviously going to be 1, because when we take the derivatives, we're going to get minus sine of s plus 8, comma, cosine of s plus 8. The length of that, sine squared plus cosine, is 1, so we're all set. Okay. Okay. If you want to see an example where things are not working, this guy's a good one. T squared sine t squared, right? If you do this kind of uncarefully, let's say we do it with s is equal to, let's start with t equals minus 1, right? Let's start where s equals minus 1 corresponds to t equals, s equals 0 corresponds to t equals minus 1. Then what's going to happen is, if you're not very careful about this, you might end up with a 2t here, dt, right? And then what would s of, again, s of minus 1 is equal to, obviously going to be 0 because you're integrating from minus 1 to minus 1, right? When you actually integrate this, what do you get for s of 1, right? You're going to get t squared from minus 1 to 1, and you're going to get 0 as well, right? So somehow you're not traveling, you're not doing an arc length, right? You actually double back and come to the same place, right? How did that happen? Well, you weren't careful around here. This actually should be an absolute value, right? Not just 2t. And essentially what happened was, because of this t squared, you're doubling back. And again, that's a problem, okay? Or potentially a problem if you're not aware of it. Okay, so I think that's a decent explanation for this s. I think starting out with s of t often gives people trouble, because ultimately we're thinking of s as a parameter in and of itself, right? We started with s of t equals integral r prime of t dt, right, roughly. But ultimately we ended up with s as a parameter. And that's really weird because we're thinking of s as a function and also s as a parameter. So let me give another kind of explanation for this whole arc length parametrization procedure. And if that first one was really weird, maybe this second one perhaps could make more sense. All right. Okay, so here's my second point of view. So we're starting out with a regular, sorry. What happened here? Sorry, let me fix this. Okay, so we're starting out with a parametrization, R of t, again, just a regular parametrization. So these evenly spaced marks go to something that's perhaps not evenly spaced because you're driving fast and you're driving slow, then you're driving fast again. Okay, so this is not an arc length parametrization. All right, what do we want? We want a parametrization where evenly spaced marks here, right, go to evenly spaced marks here, evenly spaced marks here. So maybe something like this, something like that. All right. Okay. So essentially, what we want is, you can see with this left-hand side, we've gone from, let's say, from here to there, right? That corresponds to motion from here to there, from here to there, right? But what we actually want is to start here. We go 1, 2, 3. It should be 3 hash marks, right? So 1, 2, 3. We should be that guy should correspond to there, right? In the ideal parametrization. Okay, so we can think of this as actually doing a correspondence between these two guys over here, just on the number line. All right. So again, this first number line represents kind of our original parameterization t. This second number line is going to represent the parameterization that we want s. Okay, in a way. So what we want is actually these 4 hash marks to actually correspond to this interval over there. All right. So we should have, in a way, we should have 2 extra hash marks in here like that. All right. So the way we can kind of think of this is we need to find a correspondence between our two times where this guy goes to here, this guy goes to there, this guy goes to there, and that guy goes to there. All right. And what we're going to do is we're going to do a composition. So we start out over here in S with S as our parameter. We're going to go S of 0 goes to there, and then we're going to travel through R, right? Just as before. Okay, so this point of view is very similar to the one before, but it's slightly different. Okay, when S is 1, that corresponds to R equals, this small number here, and then we're going to pass to right there. Okay, maybe I should make the first one a little more accurate. Right, so we actually pass to, for the first one, we actually pass to the start point, right? Now for the second one, when S was 1, R was something small, and when R is something small, we're not moving as far as we did before, right? We're moving only a tiny bit, okay? And so each of these hash marks here, again, with S, correspond to a hash mark on T, and then we travel to the curve using R, all right? So what's going on here is, what we're trying to find, essentially, one way to put it, is we're trying to find a function from numbers to numbers, from R to R, so that we can get the hash marks in the correct place ultimately. All right. So let me put it like this. So we have hash marks here. This is what we want. This is the parametrization that we actually have, and this guy goes to the curve via R. All right. So our messed up parametrization. So what we want is a function here. We want a function f. All right. The variable we're wanting ultimately is s, right? And what we want is when s moves 1 step, right here, it's going to move the appropriate amount of space via f to the r, to the second copy of r of the real numbers, right? And what I mean by appropriate space, the appropriate space is where, if this guy goes to here, right, then that guy is going to go to exactly 1 step away. All right, so that the composition of my functions, I do f first and then I do r. What I want is my composition to be arc length. All right. So ultimately, the way we phrase this in the second point of view is we're looking for a f. We're looking for the correct f so that this composition function has the correct properties of arc length parametrization. In other words, it has speed 1. Okay, so let me write that out in terms of math. So our new parameterization, R1 of S, is going to be the composition. We do F first, so F of S, and then we take that result and we plug it into R of F of S. All right, and that's perfectly legit because F of S, F is a regular one variable calculus function. So F of S is a number, and then we're plugging a number into R, which makes perfect sense, right? That's what R takes, right? And then the output is a vector, which is what we want, right? The output to be on our curve. Okay. All right. So this is our new parameterization, and we're looking for F so that their new parameterization satisfies the properties that we want. Okay. And what is the property that we want? The property is that its speed should be 1, right? We want F so that R1 prime of S is equal to 1. Okay? In other words, that's the same as saying, well, what's R1 of S? It's literally this composition formula. So that's R of F of S, whole thing prime should be 1. The length of that should be 1. Okay? All right, but what is this? Let's calculate the inside. This is why we talked about the chain rule in the last section. We're going to use the chain rule on the inside. We're going to take the derivative of this composition. That's going to be R prime of F of S times F prime of S, and then length of that should be 1. All right, and again, everything here is perfectly legal. F prime of S is a regular function. So if I plug in any particular S, F prime of S is just a number. And R prime of S is a vector. So this multiplication right there is actually scalar multiplication. All right, so everything is perfectly legal. Okay, now let me make a simplification just for the purposes of this discussion. Let's say F prime is always positive. All right, so in other words, in terms of our parametrization, we're saying that we want as S, we want S to move in the same direction as our original parametrization. Okay, so that if our original parametrization moves along the curve in this direction here, then S will also move in the same direction. Okay, if F prime were negative, we would be moving in the opposite direction. All right, by the way, you can see the problem. When F prime changes from positive to negative, that's going to represent turning around, right? So we definitely don't want that. So what we're actually looking for is an F that's 1-to-1, all right? Okay, in any case, let's kind of make our lives a little more simple for the purposes of this discussion and assume that F prime of S is positive. So we want F prime of S to be positive so that it moves in the same direction as our original parameterization. Ultimately, if we want something that moves in the opposite direction, we can just find this particular parameterization and then just replace all our S's with negative S, and that's the opposite direction. Okay? All right, in any case, if F prime of S is positive, if we want the same direction of motion, then we can do this. Right, we can just pull it out of the absolute value because it's just a number. All right. Okay, now I'm going to integrate both sides. Okay, so I'm going to integrate both sides, and the reason I'm doing this is because the right-hand side is super simple. All right, why was the right-hand side super simple? The right-hand side was super simple because what we wanted was the speed to be 1. All right. Okay, so we end up with the integral R prime of F of S inside absolute values. F prime of S, I'm integrating with respect to S. That's the only variable we have in this whole thing, right? In this sequence of equalities. And again, just for simplicity's sake, I'm going to go from 0, right? I could do any number down here, A to whatever I want up there, but let me go from 0, all right? 0 to S. Okay, so that makes it so that on this right-hand side, I'm integrating from 0 to S of 1, right? And it makes it so that that's just S on the right-hand side. Okay. All right. So that's S is kind of what we're, in a way, we're looking for. That's the nice simple S right there. Okay. All right. Now, this left-hand side looks kind of nasty. But actually, this f prime of s is really great because I can do u substitution with it. U equals f of s tells me du is f prime of s ds, right? So when I do this u substitution, that f prime just goes away. This is just r prime. I should put an arrow on top of that, r prime, of u, right? F of s, u is equal to f of s, du. Okay. All right. What's the limits of integration? 0 and f of s. Okay. All right. And on the right-hand side, we still have s. All right. It's pretty important that that becomes f of s, right? Because u is equal to f of s, right? So when we have a limit of integration up here, let's say of 10, right? Then this guy up here should be f of 10. Okay, and I've again done another bit of making things simple where I'm choosing maybe we this technically let's write f of 0 here just to let's not make it too simple, right? So when s is equal to 0 up here in this integral, f of 0 is equal to u, so that should be f of 0. All right. Okay, in any case, the important feature here, the f of 0 doesn't bother me too much because it's just a number, right? Ultimately, when we find f. But what we do see here is f of s on the other side. Okay, so we have an expression here on the left-hand side. This is an expression, some horrible, very likely very horrible expression in terms of f of s, right? Perhaps something like f of s to the 1/3 plus 3 fifth root of that, right? Something in terms of f of s, okay? The right-hand side is just s, all right? So what we see here is a situation where because we have all f of s's on the right-hand side and s is on the left-hand side, we can now solve for f of s as an algebra problem, all right? So just think of f of s as a variable, right? And you're solving for f of s by throwing everything else to the other side, okay? If you think about this in the right way, what we've actually done is this equation, let's say this horrible equation here in terms of f of s, that's equal to s, right? This equation actually represents the inverse function of f. What we've actually found here is the inverse function of f, right? Remember when we solved, maybe in high school, when we solved for inverse of functions, right? Let's say you have y equals x cubed plus 1, right? In order to find its inverse, you solve for x, right? So this is a very similar idea here, right? So I guess, let me say, the way we did it was, right, we swapped the variables just to make our because we're more comfortable working with solving for y's, right? Equals y cubed plus 1, right? So this represents our inverse function. And actually, it was good I wrote this down because this x is like that s over here, right? And this y is like our f of s, okay? So back in high school, when you solved for the, when you solved this equation over here, right? You were solving for y, which once you've swapped the x and a y, you were solving for the inverse, right? So this equation here is the inverse of the inverse in a way, right? So up here, it's the same idea, okay? So we're actually given the inverse function, and we're trying to find the function itself, okay? And if we do that, do that solving, then we get our f of s. And if we have that f of s, then we have our parametrization, because our parametrization, remember, was just a composition, all right? Okay, for example, let me just do it with this made-up example here. So let's say it turned out, after we did our integration, that we ended up with square root 5 here, f of s to the 1/3 here, plus 3 is equal to s, okay? Then what we would do is now we would solve for f of s. So I would say f of s to the 1/3 plus 3 is equal to s to the 1/5, s to the 5, right? And then f of s is equal to s to the 5 minus 3 to the third power, okay? All right. So what does this do? This tells me I'm done, because now my arc length parameterization is, right, the whole point of this was that our arc length parameterization was this guy right here, R after F, right? And so I just plug in F, the F that we found, into R. So the R of S to the 5 minus 3 cubed. Okay. So that's going to turn out to be my arc length parameterization. And again, if we had done this, we would actually have the formula for R, right? Okay. Now, of course, this is the same thing as if you thought about it in our first kind of point of view, because if you look at our first point of view, this would have been what we called our T. All right. And ultimately, again, how did we do it? The parameterization, we had to solve for our T, right? Because remember, we had T in some horrible expression, right? And then we threw stuff to the other side to solve for T. Okay. So this is a different point of view for the exact same thing, but I very much like this one, because it kind of boils down our entire problem into just thinking about finding a single variable calculus function f, right? And then just using the property that we need, right? We're looking for this velocity equals to 1. That means that f has to satisfy certain properties, right? In particular, this property down here. And so that allows us to find f by doing the algebra. Okay, and again, I really like this one as well, because it explicitly shows us that the T, the first version, what we were doing was we were actually finding the inverse function of the composition function that we actually want. All right. So let me do a kind of application of this, a kind of more theoretical application. All right. Oh, I forgot to say something. Back here. Sorry about this. When I integrated here, right? When I integrate from 0 to s, that just popped out an s, so I don't have to worry about a second term, right? So I have a 0 here and a 0 there, right? When I had f of u there, right, that was choosing the start point of my new parameterization, right? If I wanted to shift my start point, that would be reflected in this f of 0. Okay. All right. Now, let me talk about why we care about, or at least one example of why we might care about arc length parameterizations. So let's say that R of S is an arc length parameterization of a curve. All right. So say that we've already done a lot of work. We found an arc length parameterization of some curve. All right. Okay. What's the point of this? The point of an arc length parameterization is that R prime of S is equal to 1. Right? So arc length, R prime is equal to 1. And again, always keep in mind the picture. Arc length parameterization means every time I move one step here, in terms of my curve, I'm moving kind of equal amount of distance per step in time. Okay. Sorry about that. All right. So speed is 1, right? That's the major feature of an arc length parameterization. My speed is 1. This is great because this right-hand side is a 1. Again, we already saw that was great in the above discussion, but it's great right now because it's a constant. Why is that great? Because what I'm going to do is I'm going to differentiate both sides. All right. I'm going to take dds of both sides. And of course, the right-hand side is 0. All right. Okay. Now, sorry. I wanted to make it even easier on myself. Square is 1. So now I don't have to deal with square roots, all right? So square is 1. If the length is 1, the square of the length is 1, right? So square, okay? That's gonna make my life a lot easier in 1 second. Okay, no difference, right? If the speed is 1, then the speed squared is 1. I differentiate both sides. I get the derivative of the speed squared should be 0, okay? But this left-hand side I can simplify, all right? This left-hand side is DDS of r prime of s dot r prime of s. Okay? Right? Remember, the length squared of a vector is the dot product of that vector with itself. Okay? All right. And you can see that from the definition of the dot product. Okay? All right. So I'm differentiating this. By the way, everything at this moment, at least in the first line above, this is one variable calculus above, because I'm taking the derivative of a one variable function, because the speed is a one variable function. Okay, now is where kind of the vector stuff comes in. When I take this derivative with respect to a dot product, right, this is the product rule that we talked about last time, or maybe it was 2 lectures ago. This is going to be r double prime of s dot r prime of s plus r prime of s dot r double prime of s. Okay, just a product rule. Okay, now these two guys are actually the same. This is equal to 2 r double prime of s, r prime of s. All right. Okay, what was the point of this? Well, originally, this thing is equal to that, is equal to that, is equal to 0. All right. So what we have is, I can divide by 2 on both sides, right? So r double prime of s, sorry, I should emphasize, this is a dot product, right? So r double prime of s dot r prime of s is equal to 0. Okay, so if you have an arc length parameterization, then this is my conclusion. This is my velocity. Again, thinking of this in terms of motion, this is my acceleration. Right? So if you have an arc length parameterization, so if r of s is an arc length parameterization, then velocity dot the acceleration is 0. In other words, velocity is perpendicular to acceleration. Right? Dot product equals 0 means perpendicular. Right? Okay. Now, sounds kind of neat, but who cares? Right? Well, we care because let's take a look at a picture. Let's say my velocity is in this direction. Right? Let's say I have an arc length parameterization, right? Yeah, my velocity is in this direction, and we have an arc length parameterization, so my acceleration is perpendicular to it. All right. Now, without knowing anything about my actual formulas or my curve or anything like that, I can tell you that my curve looks something like this, curved in this direction, as opposed to something that's curving in that direction. Right? Why? Because acceleration is the change in the velocity, right? So if my acceleration is pulling this way, that means my velocity is being pulled kind of towards, maybe this direction, then that direction. It's being pulled downwards in a way, right? And so that means as I travel along this curve, I have to be kind of curving downwards as I travel, as opposed to curving upwards, like in the picture above. Okay, so here I'm curving downwards. I'm being pulled towards this arrow right there, towards the acceleration, towards the head of the acceleration arrow. Okay, so if I have an arc length parameterization, I can very, very easily get information about my curve. All right. Okay, so in a way, one way you can think of this is I can very easily get information about the road I'm traveling on, right, when I have an arc length parameterization, as opposed to if I didn't have an arc length parameterization, if I just look at A, that would have information about not just the road, but also how I'm driving along the road. right? For example, A will incorporate, if it's not an arc length parameterization, A will incorporate not just my motion along the road, my motion kind of, A will incorporate not just the curvature of the road, how the road is curving, but it'll also incorporate how I'm accelerating as I'm driving forward, as I hit my accelerator, right? So A will be kind of like a skewed vector, perhaps like this, because maybe as I'm driving, I'm speeding up, right? So not only is the curve coming in a factor of the road, my speeding up is also a factor. So my A, when it's not an arc length parameterization, doesn't just give me information about the road. It gives me information about my driving and the road, right? But if it is an arc length parameterization, the A vector, in a way, gives me information purely about the road, right? Independent of my driving, okay? So what that means is if I have a curve, right? If I only care about the curve, or in other words, I only care about properties of the road, right, and not about motion along the road, then what I should do is I should find an arc length parameterization, and then when I calculate the A's of that arc length parameterization, those A's will purely be intrinsic information about the road, right? And again, if I do just a regular parameterization of the same road, my A's are going to be, right, not just information about the road, but information about the road and my acceleration, right, about how I'm driving along the road. So when I'm just interested in studying the road itself, right, when I'm just interested in studying a curve, but not necessarily how someone's moving along the curve, I really would like to work with arc length parameterizations, okay? Especially on a theoretical front, as you can see, right, when you do stuff with the arc length parameterization theoretically, you end up with really, really nice formulas like this dot product right here, okay? All right, now what happens is 14.5 is essentially about this. 14.5 is about curvature, right? If you read 14.5, they'll tell you terms like curvature, right? Something like that, torsion, stuff like that. And that's studying intrinsic properties of the road, of the curve, right? And essentially curvature is basically my acceleration, all right? It's not literally the acceleration, but it's essentially the same. If you look at the book, right, the information that the curvature gives you is exactly the same information that A gives you. It's expressed in a different way for various reasons. So curvature is not just literally A, it's something in terms of A, okay? But if you look at the formula, it'll be roughly A, right? It'll have, not roughly A, it'll have A's in the expression, right? Because it essentially gives you the same information as A, all right? So 14.5 is basically about studying properties of curves using, well, if you want to make your life easier, using arc length parameterizations, and then defining various terms out using that. Okay. All right. We're going to skip 14.5. We're going to skip it because I think most of us who take this class don't really need stuff like curvature. And if you do need it, for example, if you're a math major, you'll learn it again in a future class for sure. All right. So I think most of us probably are going to be engineers or something like that. And so this is not something that's perhaps relevant to us, certainly at this moment. So I'm just going to skip it. And what we're going to do next is, for next week, we're going to move into chapter 15. All right. And that's going to be multivariable functions for real. All right. Where you have multi inputs. Okay. All right. But that's it for chapter 14.